Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So welcome everybody, and it's a pleasure to introduce Angelina from Duke, who's also done postdocs at MPI and elsewhere. So
University of Vienna.
Yeah. So and also been locally in Oxford briefly as well. So Angelina, it's a pleasure, and she's going to talk to us about mechanism design for cloud computing and crowdsourcing. So Angelina, over to you.
Thanks so much for the invitation. I'm delighted to visit Microsoft Research. My talk today has titled Mechanism Design for Cloud Computing and Crowdsourcing. Let me first give you an outline of my talk. I'll first give you an introduction to some basic notions that will come again and again throughout the talk. Then I'll talk about the problem of scheduling selfish unrelated machines and discuss the following aspects of it. I will give a geometrical characterization of truthfulness. I will discuss how you can get lower bounds for truthful mechanisms. And finally, I will discuss characterizations of truthful mechanisms for this problem. Then I will switch gears and present a scheduling with uncertain execution time problem, where machines do not know their processing times. It's again a scheduling problem though. And finally, I will give you I will tell you about some of my future research plans that have to do with cloud computing and crowdsourcing. And these tie very well with the previous problem. So I believe that whatever I will present about the first problems is a solid background for the last part. So we want mechanisms that are truthful. We want mechanisms that don't give players an incentive to lie. Let's consider a situation when a player has an incentive to lie. One day before the elections, the two big parties are in duel. And you have Captain Haddock, who's a true fan of the Green Party. And he sits and thinks, should I vote for the Green Party? Or should I vote for determining who's going to be in the government? And it turns out, since he prefers the Red Party to the Orange Party, he can determine the outcome of the elections. So he should vote for the Red Party and achieve a more preferable outcome by lying about his preferences. So in mechanism design, generally we face a situation where we need to make a single choice for the whole society. In voting, we need to select a single winner of the elections. In public projects, we need to decide, are we going to build that bridge or not? In auctions, we need to decide who's going to win the item and at what price. And in scheduling, we need to decide which machines are self-scheduling, which machines are going to get the tasks, and what are they going to be paid. In all these settings, we want to construct a function that takes as input the preferences of many different individuals and aggregates them, amalgamates them into a single preference or choice. And despite the fact that someone might not agree with the outcome of this function, if you construct, if you design a game, if you give such payments, such incentives to the players, so that the outcome of the mechanism is an equilibrium, then they don't have a reason to deviate. So that's the whole idea of mechanism design. Even though the people might not agree with the solution, they don't have an incentive to deviate from it. And the most famous example of a truthful mechanism is the Vickrey mechanism. The Vickrey mechanism applies to many settings, but the most simple example of it is a single item auction. The bidder who bids the highest wins, and he pays the second highest bid. It is just that simple, and it is truthful. So, since the winner, say the winner has valuation 10, since he's anyway paying 8, he doesn't have an incentive, say, to report 9 and still win the item. You see what deviation you could do if you would use a first price auction. And it applies to many settings. You can apply it for many items. But however, for some settings, like combinatorial auctions, it's computationally inefficient. And if you have a different objective other than maximizing the welfare, maximizing the happiness of the players that participate in the auction, then it might not perform well, because the Vickering mechanism is actually the mechanism is equivalent to the mechanism that maximizes the welfare. Like there exist payments afterwards that make it truthful. So if your objective is not this one, you might need a different mechanism. Now let's move to the scheduling selfish unrelated machines problem. So the setting is the following. You have many players, n players, and m tasks. And the input to the problem is a matrix of processing times, where the entry Vij is the time that player I needs to process task j. The objective here is to minimize the make span. The make span is exactly what you can see in this picture. If a lot of machines process, it's the time of the player who finishes last. And the output of the mechanism should be an allocation of the task to the players and payments. The players will not process the tasks if they don't get paid. So if we didn't use any payments at all, they would just tell us that they can't do the tasks. And that would be their best bet.
I see that the matrix says how long they will take. But how do we determine how much they get paid?
Actually, in this problem, it's again one payment for each player. Like there is an the output is an allocation matrix, so you have an entry Aij for its Aij, which is either 0 or 1. The player gets a task or he doesn't get it. So the allocation matrix is again a matrix like that, and the payments are one payment for each player. Actually, in this problem, it turns out that the payments, we can concentrate without loss of generality on the allocation part of the mechanism, and that's why I said the Vickering mechanism is equivalent to the mechanism that maximizes the welfare. And if you know that, you can find truthful payments. So if you have an allocation rule that is truthful, that satisfies some properties that make it truthful, then you can find truthful payments too. Yes?
Why are you trying to minimize the completion time rather than trying to maximize something measured in dollars?
Something?
Measured in dollars, something relating to earning. Seems to me, it's not obvious, is it, that the objective function would be which is the last task to finish. I mean, that's one possible objective function, but there are
you could minimize the sum of the processing time, say. That's
more likely. I mean, usually you want to maximize something which eventually is in the units of dollars, in the units of money.
You mean like maximize revenue or
some kind of revenue, maybe for
all of this makes sense, but it's just a different problem. But you'd certainly gain intuition from one problem to the other, like revenue maximization. Say the Vickering mechanism again is truthful, but with a reserve is the solution, but with a reserve price.
As we're interrupting, do you plan to define welfare at some point?
No, it's just the happiness. I'm gonna do it now. Thanks for the question. It's the sum of the values of the players. So welfare is actually the sum of the values of the welfare in this problem. In auctions, welfare is to give the task to the players that will maximize the sum of the valuations. You have a sum of the valuations of the players who get something. That is a single item auction, so it's very easy. You just give it to the player who is happiest getting it. That is the welfare. If you have many items, the welfare would be to give the items to such players so that the sum of the happiness of the players is maximized. That's welfare.
And welfare is V because the auction is fair or truthful or whatever that word was.
Welfare is V. What?
V was
V was the value on the previous slide. So because
actually here you can again, I might say welfare it's again to minimize the sum of processing times. So scheduling and auctions are basically two sides of the same coin if you don't concentrate on the allocation rule. So if you have, say, all possible mechanisms for scheduling, you have all possible mechanisms for auctions, self-scheduling.
I guess it's interesting to be able to be general about welfare functions, isn't it? So that
Be general in what sense?
Oh, to allow a third party to specify what they consider to be the welfare, and then for you to be able to say, well, here's the mechanism that will do it.
I would call that objective. Like, you could have different objectives. Welfare is one, revenue is another, makespan is another. And for all the settings, we want mechanisms that are truthful. So studying truthfulness in general helps us deal with many different settings and many different objectives. And the best mechanism we have is the VCG mechanism that maximizes the welfare. That's the simplest, and sometimes it's too lonely. Sometimes we can find many other mechanisms that are truthful. So we try to approximate things by using the Vickrey mechanism, even in settings where we have a different objective. Okay, so in this, getting back to this problem, player I is the only person who knows the values of that are in row I. And since he's selfish, he can choose to report false values. And the allocation is 0 or 1, 0 if the player doesn't get the task, and 1 if he does. Okay, what's wrong with the Vickrey mechanism? We just said that that's the thing that we know. Let's try to apply it. Suppose that we have this input matrix. So there is one guy who is slightly, epsilon is positive. You have one guy who is slightly faster than everybody else. He's going to get all tasks. And he's going to take 3 units of time, n units of time if you have an n by n input.
The Vickrey mechanism would mean each task is auctioned independently and each player bids for it, and since this guy is faster on all of them, he'll win all of those independent auctions. Is that right?
It's great that you got it. Okay. I'm very happy. That's exactly this case, yeah.
But I wasn't at all sure that's what you meant.
Yeah.
It's too stupid.
So one way, there are 2 ways to generalize the Vickrey mechanism. You can either run it on each task separately, or you can say it's the mechanism that maximizes the welfare, where the welfare is what we agreed before it is. And the 2 are equivalent. And it's awesome that you just made this remark. So yeah, here, and that's because the valuations are additive. If you didn't have additive valuations, it would not be the case. Like in a combinatorial auction with non-additive valuations, this would not be the case. Like in scheduling, if a guy, like the time the first player takes to process these 3 tasks is the sum of the values. So if it would be something like subadditive or submodular, then it wouldn't be the case. But yeah, that's a great observation. And the optimal thing would be to parallelize the tasks and to just take 1 unit of time. So that's why the Vickrey mechanism doesn't do well in our case, and it has an n approximation to the makespan objective that we chose. So this problem is very important in the area of algorithmic mechanism design. And the reason is because it was proposed in the paper that founded the area, and it also combines characteristics from the 2 areas of which algorithmic mechanism design consists, economics and algorithms. It combines the very important problem of combinatorial auctions with a classical scheduling problem, the scheduling unrelated machines problem. And I just showed you that the Vickrey mechanism achieves an n approximation. And the best, and the lower bound that we know is only 2.6. So it's open what is the best approximation ratio that we can achieve. The conjecture, by the way, is that the upper and the lower bound is n. That's what people believe. But then you never know. Let's define truthfulness again more formally. So fix the values of the other guys. Do I have an incentive to deviate and lie or not? Players are utility maximizers, and we assume that utilities are quasi-linear. So we assume that utilities are valuation minus payment. So a mechanism is truthful if a player who has type V doesn't have an incentive to report type V prime, to lie, and to produce another allocation. Here I'm hiding something. Maybe you got it again.
No, I'm still reading the first line. The utility of a player is value on
Of the allocation, say time spent processing.
Minus something. What's this?
The payment.
But he doesn't pay anybody. He gets paid for doing the job, doesn't he?
Yeah, that's true.
Subtracted.
Because it's more common in auctions. I mean, it's the other way around. It's the same thing.
And what's V minus I? V subscript minus I?
Or am I describes the valuations of the other players? Yeah, that's again a very good observation. Like it's true that it's payment wise valuation, but you either minimize or maximize, so it's fine.
I still don't understand that line. Maybe it doesn't matter.
No, you got it right. It's payment wise valuation. If you want to maximize it. If you want to minimize it. You got actually a typo in my slide. You got a typo in my slides. That's minimize. I mean, it's either minimize the minus or maximize the. Yeah, because the sum.
The valuation of the other players. Is there some sum over the valuation of the other players involved here? Is there a sigma missing? I don't see. So if there's one, if I is 3, yeah. What is V minus 3?
It's a matrix of processing time. So here you take out the row of player I, and V minus I is the rest of the values. That's it.
Its data type is vector. What's vector things?
Actually, here it's a
matrix.
It's a whole matrix here.
With one row missing.
Yeah, I'm gonna use the notation here. I'm gonna use the notation. That's better. So here's the input. It's a matrix of processing times. I use valuations to remind you that it's the same with auctions, right? And here's the output. It's a matrix of 0, 1 values. You get or you don't get the task. And the vector, this is the vector of player I, and I denote it by VI. I skip the vector notation because it gets ugly, but it's mathematically sound because I use a different letter. Okay, and truthfulness is equivalent to this condition. This condition has allocation and input, like valuation and allocation. So you take one input and its corresponding output, and another input and its corresponding output. The two inputs differ only on line I, right? They just differ on player I. One player deviates. That's the situation we are trying to consider here. Then, if you just look at these row vectors of player I, forget about the other players, fix the values of the other players. That's V minus I. That's your matrix that you asked me about. These row vectors have to satisfy this inequality. And if you don't understand it, I'm going to start explaining it to you more intuitively. But it's called monotonicity, and it is a monotonicity. Like for a single task, it's that the allocation is monotone. So it's monotonicity for a multi-dimensional setting. So this condition is necessary and sufficient for truthfulness. And here's the geometrical interpretation. Let's say that we have a single task. It tells us that the allocation should be increasing with respect to the value of player I when we fix the values of all other players. And because the allocation can either be 0 or 1, if you have a small, if you can process the task very fast, you have a small valuation, you get the task. you get to process it. Then there is a threshold, and that depends only on the values of the other guys, of the other players, and your your allocation changes once and for all from 1 to 0. This mechanism is not truthful. Why isn't it? Well, we have to find a deviation. Say this guy here doesn't get the task. Wait, no, this guy here gets the task. Sorry. Okay, I'm gonna choose this one. This guy here doesn't get the task. He wants, if he reports a higher value, that it takes him more time to get the task, he can get it. Like this would be the deviation. In an auction, it's like you could pay less and you could still get the item. That's the equivalent in an auction. So there is a deviation if it doesn't have the threshold behavior. So that's how I would like you to remember monotonicity. It's monotonicity, how we say it in calculus, and it's this threshold behavior. Yes?
This seems to make the crucial assumption that your payment is independent of your value, right?
Yeah, I can prove that.
I mean,
it depends only on the allocation. It depends only on the allocation. And the proof is very similar.
But it's very natural in the scheduling context to make your payment depend on how long you took to process the item, right?
It's not going to be truthful otherwise.
Well, I'm just saying that has to be stated up front.
Yeah, that's an awesome observation. It's a lesson I was trying to hide you. Yeah, but I can prove that any truthful mechanism has this property that you just noticed. Okay, and let's say we have two tasks. How does monotonicity look like? It's again a threshold that separates, that gives the slope of the separating hyperplane between two different regions. Like here it's the region where the player takes both tasks, and here it's the region where the player gets just the second task. Monotonicity tells us that this is the separating hyperplane. And if the two allocations differ on two tasks, then it's going to be a sloped line, 45-degree sloped line. And if we put everything together, we get that all possible shapes are these, and they're you can just translate them. I just need the shape to be like that. I just need this generalization of the threshold behavior that I had before. So the region here it's this is the input space, the value of the first task, the valuation of the player for the first task, the valuation of the player for the second task. So this is my whole input space. That's what the mechanism has to give allocations to. And these shapes show which allocations correspond to which part of the input space. So the truthful mechanism has to partition the input space in a very specific way. And it can only be this for the case of two tasks.
The axes here are the valuations of one player for the two different tasks.
For the two
Assuming
different tasks?
that the other players have everything fixed.
Great.
Okay.
No, it's awesome that you're following me.
5 degrees, is it?
Yeah.
Okay.
Yeah, that's all. And actually, if you think of it from a geometrical point of view, if you rotate one shape, you get the other. And the previous, the one that looks more like a threshold mechanism, that I will call it later a threshold mechanism, this is a degenerate version of the other two, because you can contract the two nodes, right? Okay, what's the geometry for 3 tasks? It looks like that. And that's up to rotations, like that. All these shapes, if you rotate them, you again get the truthful mechanism. And you can also have the degenerate versions of this. And a nice observation is here that the projections are these 2D shapes, and you have either the one of them or the other. I will just give you 2 hints about the ingredients of the proof. Monotonicity has to do, if you want to prove that monotonicity is necessary for truthfulness, You have to consider a situation when a player has valuation V, and the mechanism gives allocation A, and he deviates and reports V prime. And another deviation when his true type is V prime and he reports V. There is a way to give weights to this graph. I won't tell you how, but monotonicity is equivalent to saying that the graph has positive weight. And actually, this condition is also sufficient for truthfulness. That's why I never talk about payments. And for a very nice proof of the sufficiency, you can see one of Ian's papers.
What are the nodes and edges of this graph? They seem to be pairs of a value and an allocation.
Yeah, so here it would be the allocations. Sorry. You can just think of it as allocation, basically.
That's just 0 or 1?
Yes.
So there's just exactly 2 nodes then?
Yes.
No, it's a vector. No.
No, it's one node for each region of the previous shapes that I gave you.
One node for each region. Okay, what are the edges?
The edges are something that is the difference of the two allocations times the valuation. It is basically, if you look at the monotonicity property and you rearrange it, it's AI minus AI prime times VI, this part.
Is that
Yeah. It's actually the supremum of that for the whole region. But you're asking too much. I was not planning to confuse you with all those details. And another proof idea, and I'm going to be done with the geometry of truthfulness section, is that you have these complicated polytopes, and the way to deal with them is to look at the boxes that contain them. And if the boxes that contain two regions intersect, then the two regions share a common boundary. And you just so you have just to study the distances between the boxes. Using cyclic monotonicity, you can compute which these are. Okay, I'm gonna get to the lower bound section. Okay, so we just saw that the V-Cray mechanism is an approximation to make span, and I'm gonna show you how you get the two lower bound on truthful mechanisms. You just consider that was actually in the paper that founded the problem, and it's pretty simple compared to the 2.6 lower bound. So you just consider this input, and you use this observation. So the general idea behind lower bounds is that monotonicity restricts the algorithm that we can use very much. You already saw it in terms of the shapes. Like the shapes are very specific. It's not that you can partition the input space any way you like. In order to get lower bounds, we will focus on pairs of different inputs and their corresponding outputs. And we will see what the allocation of one instance means for the allocation of the other one. So we will basically use this very simple observation. You can prove it using the monotonicity property. If a machine gets a set of tasks, like here, say that the red tasks are the tasks that are allocated. Machine 1 gets these two tasks, and it becomes machine 2. Machine 2 gets this red task, and it becomes even faster at it. Its value gets from one moment to 0, so you can say epsilon, a very small amount. Then that is V, and the A is denoted by the red values.
Okay.
Yeah, sorry.
Right, a new encoding, right, fine, okay, I'm with you.
Okay, so the second player gets the first task, and he becomes faster at it. If he becomes faster at the tasks that he got, then he still gets them. That you can prove using the monotonicity property. And generally, if you would get more tasks and you become faster in the ones that you got and slower in the tasks that you didn't get, then the allocation doesn't change. And here I'm hiding you some epsilons that you have to take to be careful about, but it's basically this. So you start with this instance, and using this property, you just consider these two possible allocations, and using this property twice, you again end up with this way of proving lower bounds. But you cannot do that for matrices that have more players. So the way to get the 1 plus the golden ratio lower bound is to consider an input like that, and to consider the two cases. The one is when one player gets all tasks. That's what the VCG mechanism would do. The Vickery mechanism would do. Oh, actually, A is here a variable, and we will solve for it so that we get the best lower bound that we can. It's gonna be the golden ratio, but we're just keep it a variable in the beginning so that we can find the best possible value for it. And the best possible value for it is determined by balancing between performing bad in these two situations. The one is when one guy takes all tasks, and the other is when at least one task goes to another player. So if one guy gets all tasks, the best thing to do would be to parallelize the procedure and to have a diagonal allocation. And the ratio of the cost over opt is this one. It's this geometric series. In this other case, we can prove using complicated induction and strengthening the induction hypothesis that the approximation ratio of the mechanism is at least 1 plus alpha. And solving this equation, you will get the golden ratio. So it's basically, in order for the mechanism not to perform bad in any of the two cases, you have to make these two quantities equal, and you get the lower bound.
So, if I understand this right, you're saying that at the moment we don't have any particular mechanism in mind. You're saying that any mechanism that guarantees monotonicity or truthfulness
exactly
could be as bad as, or in fact will never be. No, there would be some problems for which it would be as bad as 2.5 times worse than.
There will be some instance for which it will perform badly, like it's worst case analysis.
Okay. Well, maybe we should give up on truthfulness. Maybe we could do better if we didn't have truthfulness, right?
But we just have proved the 2.6 lower bound and the upper bound is n. It's wide open.
But if we didn't insist on truthfulness, maybe we could go, maybe our lower bound would get better.
What would be your alternative for truthfulness?
I don't know yet, you're the expert. I mean, you've just said truthfulness is a kind of, just something you assume is good.
Yeah.
Right? But it forces this bad result on you.
Yeah.
So maybe you should question the assumption.
There are several ways to question the assumption. You can either look at MV-free mechanisms, or you can look at fractional allocation or randomized allocation. But for most of these cases, the situation is very similar. The NV-free case has been solved, and NV-freeness is pretty similar to truthfulness. But again, you don't get a constant. You never get a constant approximation. And the fractional and the randomized version of the problem has exactly the same behavior with different proofs. So. Okay, so we did just as good as 2.6 for the lower bound. We have this huge gap. So, and we only know one mechanism, the Vickery mechanism. Maybe we know a few more. Can we prove that these are the only possible mechanisms, or can we start finding other mechanisms? So the Vickery mechanism, I would like you to remember the Vickery mechanism for multi-parameter settings as the mechanism that maximizes the social welfare. And that's enough, because I told you that the payments are, if you have a truthful allocation, you can just concentrate on the allocation part and forget about the payments. And you can generalize the Vickery mechanism in terms of affine maximizers. The affine maximizers just take the objective of the social welfare and optimize a weighted social welfare. Remember the geometry we discussed before? The Vickers mechanism allocates each task independently. That was your observation. That you look at its column and you allocate its task independently. The geometry of tasks of mechanisms that allocate its task independently looks like that, because there is a threshold. You get the first task, you don't get it. And a fine minimizer might look like that. So it's much more general in terms of geometry. And except for these mechanisms, the Vickers mechanism and its generalization, we also have threshold mechanisms. These don't allocate exactly its task independently. That would be allocating its task independently. They still have the shape. They still have a threshold for each task that does not depend on the other task. And if you ask me which values can affect the allocation A12, it is these red values. So it's no other value of player 1, but it might be the rest of the matrix. And these are... Why what?
So you said something influences something else for some reason.
I said that you do not need necessarily to just allocate its task independently. You could use this value to determine if player 1 gets task 2 or not, which is the value of player 1 for the second task. It sounds irrelevant, but I'm just looking for all truthful mechanisms. So I'm trying to find, even weird mechanisms. That looks weird. I mean, it's not going to help us minimize the make span. But if I want to characterize, I have to think of all crazy examples. And that's what it's doing. But I think the way to think of it is that it has this geometrical picture and that it allocates its task almost independently. That these values are pretty irrelevant for allocating the task or not if you don't have the rest of the values. And for the case of 2 players, we can prove that the only decisive truthful mechanisms are either affine minimizers or threshold mechanisms. And if you have more tasks, it's again a combination of affine minimizers and threshold mechanisms.
What is a decisive
A mechanism that in the geometrical picture has all regions. Like no region disappears. I haven't shown you non-decisive mechanism. But if you would make one region disappear, it would be non-decisive. So for fixed values of the other guys, one player can achieve all allocations by bidding accordingly. It's not a big assumption, but it's pretty often used. But yeah.
So this is just assuming additive valuation. So essentially, you have just a single parameter type.
It's not single parameter by any case.
Well, but you don't have troubles with your payments unless being irrelevant.
But you're asking about the threshold mechanism. Yeah, that's a great observation. They only exist for additive valuations. They don't exist in combinatorial auctions. Yeah, that's true. That's actually the only domain where, like the biggest domain, the more general domain where they exist. Some project that I just submitted is a characterization of S-monotone mechanism. These are mechanisms that where the monotonicity property holds with inequality. With me.
Sequential way. If I was auctioning, you auction the first task, and if you win, right, then I'm going to be less keen to give you another task because some of your execution time is used up now. Yeah. Do you know what I mean? The auctioneer might become less keen to allocate something. Did you think about that? Because it makes sense. It would be strange to have completely independent auctions.
Yeah, but I mean that's not gonna be truthful if you wanted to stick to truthfulness.
Maybe.
But it's also not clear what you're gonna do if you relax truthfulness with some other similar notion. But yeah, I mean it's a natural thing to think of.
Completely independent auctions is a bit of an unrealistic.
No, it's not. No.
Yeah, it sounds to me like we were saying when you put up your original graph of the 1 minus epsilons for one.
Which graph?
You had a vertex, a matrix in which you had one row was all 1 minus epsilons.
Yes.
And you said, well, causes us to allocate all of the tasks to this one vertex, and therefore it comes out with cost n. But what you're from my understanding of this graph is that you're saying that because one of the bidders has more money and you run all of the auctions in parallel, that the bidder is able to use their more money in all auctions in parallel in order to win all the goods. But of course that's complete nonsense, right? You can't run all the auctions in parallel and allow the same bidder to use their higher amount of money in all the auctions simultaneously. You've got to run the auctions sequentially. They can run out of money, they can't just keep using the same money.
They cannot just keep using the same money. That's the part that I didn't understand. I understood the rest of the argument, and that's it's true.
Auctions sequentially. The columns here are the auctions. Right?
You can also run it simultaneously. It's just equivalent to run them.
If you run them sequentially, then after you'd allocated the first task to the agent, it would no longer have the opportunity to complete a subsequent task in 1 minus epsilon because it would already be busy. It would have to bid 2 minus epsilon or something,
then,
right?
Yes,
At which point the victory mechanism would give you your optimal outcome, right? So the problem is that you decided it was okay to run all the auctions in parallel.
I'm not really running all auctions in parallel. It's just that I have a combinatorial auction, and I want to find the welfare maximizing allocation. And I find that, and it turns out that it's the same with running all auctions sequentially.
It is.
And so I didn't have the chance, like from the way the problem was defined, I didn't have the chance to allocate it independently. But of course, it makes a lot of sense to study auctions that are sequential. But it wouldn't be truthful here. And that's not the problem I'm studying, but it's not. It makes a lot of sense, yeah. And it has been done, like for auctions. I'm not sure about scheduling. I don't think anything has been done on that. Actually, I think it hasn't been done on the full information setting.
Sorry, full information means we know the values.
Competitive equilibrium, yeah. I think I'm slightly out of time. I think I'm gonna skip this problem, unless you give me more time. Okay. Okay, so this problem is again a scheduling problem. You can also think of it for more tasks. I'm gonna just talk to you about the single task case, but you can just run separate auctions for each task and put them together, like we discussed before. Here the goal is different. It's to minimize the processing time, the sum of processing times. We have the notion, we're going to deal with the notion of uncertainty, like that's the key ingredient of this problem. So the mechanism designer is, say, the queen, and she wants a painting for her palace. And every day she can decide which painter is going to paint. And the painters don't know exactly how much time it's going to take them to finish a masterpiece, but they have an estimation of it. So each painter has the painting time that he needs to finish his painting, and it is a draw from a distribution phi. So before...
Is it one painting or several paintings? I don't understand why...
We just need one painting, but whoever finishes it first, he's gonna put it in the palace, and the rest are gonna burn their paintings or whatever. So yeah, the distributions are independent from each other, and we assume that the utility of the players is again time spent in painting minus payment. So it's valuation minus payment. And we also assume that the painters have monotone hazard rate distributions. So in the previous problem, the types were a number, the processing type. Now there are distributions. So the input of the problem is now a vector of distributions. So the monotone hazard rate says that the more time a painter takes, the less likely he is to finish. So it's like he got in a creativity, he's not creative anymore, or he's trying to do something very hard. Actually, you could think of it as a crowdsourcing problem too. So you want to solve a hard problem by running a contest. You would like to have payment 0 for whoever fails to finish a solution. You have uncertainty because if the problem is hard enough, then you don't know how much time it will take you. And the image assumption makes sense, the hazard rate assumption, because the probability of finding a solution in the beginning might be easy if the problem is very easy, but then it might take forever, you don't know. So because of the MHR assumption, we can prove that the greedy algorithm is optimal. So what the queen has to do is that each day she has to go to the painters and assign to the painter who has the maximum hazard rate. Assign to the player who is most likely to finish on the very next day, greedily. We know the Vickers mechanism. I told you so much about it, but it isn't truthful. Expected Vickers is not truthful. We have to take expectations because the types are distributions. And the example is, suppose that you have these two painters. Just look at the first time step. El Greco is more likely to finish on the first time step. He gets to paint. But he could report that he is even more likely to finish on the first time step. And the idea behind this is that it looks like that we don't really need we will not really use DALI to paint because, like in expectation, El Greco will finish at the first time step with very high probability. So in expectation, DALI's contribution is very small. So El Greco gets a bigger payment. But that's because we asked the players for their values, and then we gave them payments, and we didn't look at what they did. So the solution is to use the realized times of the painters. So suppose that this is El Greco gets to paint the first and the second day, Dali the third, and Leonardo da Vinci the fourth, and we get a finishing time here. El Greco gets the masterpiece first. So we're going to run a mechanism that gives these payments. It's minus the sum of the values of the... of course, the winner is El Greco, the guy who finishes. And the payments are going to be minus the sum of the other guys. That's exactly the gross payment, and I'm going to show you in a minute why this is the gross payment and why this makes a mechanism truthful. The objective of the mechanism is to minimize the sum of processing times, right? It is this thing. It's actually the expectation of this thing. El Greco wants to maximize his valuation. So by giving him this payment, you just make these two things equal. So that's the idea behind the Vickers mechanism. That's how I like to remember it. I don't like to remember it as a second price auction. I like to remember it as a mechanism that gives such payments so that the objective of the selfish players becomes the same as the objective of the mechanism designer. And you cannot always do that, but for the welfare it's easy to do that like that. And actually, that's also the proof that not only they don't have any incentive to lie, but they also don't have any incentive to miscompute. And it's crucial that we use...
Not only for the days that he painted, but also for the days that other people painted before he finished. That's the Grove extra bit, right? In your picture. So his payment is...
His payment is basically what he gives to society. Like how hard it would be if he wasn't there.
I was just looking at the bottom line. It looks like he gets paid.
I thought you were going to tell me that the payments are negative, which I was trying to...
That's what the saying it is.
But there is a way to make them positive. I'd like you to remember just this thing, that you just choose, you look at the objective, you look at the utility, and you just subtract the objective from the utility, and you get, so that you make these two things equal. And yeah, we devise an exposed truthful mechanism. These payments are negative, but there is a function that you can add, and we managed to devise a mechanism that doesn't pay a player who doesn't complete a task, uses the realized values. It satisfies individual rationality and expectation, so the players want to participate in expectation. It has positive payments, and it's the best interest of the players to exert full effort. And finally, a very brief discussion about cloud computing and crowdsourcing. So cloud computing has reshaped the way we see computer nowadays. It has turned it into a sort of public utility. We go to a website, we press a button, we open the tab, and we get networks, servers, storage, applications, and services that are easily configurable and on demand. And it's also a characteristic that users arrive and depart whenever they want. But why is the cloud selfish? What has game theory to do with cloud computing? What can we model using mechanism design and game theory? So game theorists would say, okay, can I model it as something that I know? Can I model it as a congestion game, as a scheduling problem, like the ones we saw before, self-scheduling? Can I model it as an auction or a market? Or maybe we need a new model, probably that, but we'll gain some intuition from the previous ones. So in this problem, we have multiple players, multiple users who arrive and depart. They have different requests. There are multiple providers. Both users and providers are selfish. The providers also have to decide an allocation, which players they're gonna service and at what price. And there is certainly uncertainty about what the demands of the players are gonna be. They have to estimate their demands. They sometimes overbook. And then, even though cloud computing abstracts computing from the physical machines, it is always a problem how to assign and efficiently divide a computer into many different virtual machines, and how to fairly assign tasks to multiple cores and memory, and decide which tasks need more memory and which need more computing power. And of course, here you're probably going to think, yeah, it's also a scheduling problem, because you need to split jobs into tasks and assign them to multiple cores. So the problems that we discussed so far can help us with dealing with some of these aspects. And then there's the question of what prices do we use. Probably all these cases are realistic, and not one of them is a good answer. So maybe the cloud provider is post their prices, or maybe there is a spot market and the prices fluctuate. Or maybe there is a negotiation, like there is an auction that is run by a big company who wants to use cloud computing services, and the cloud providers bid. And finally, cloud providers are selfish players. Why do they have an incentive to be accountable, to be responsible as a company? So maybe we need an external authority, an external trusted authority that has something like a rating system, or gives them incentives that in order to be accountable. And this is my last slide. So crowdsourcing and crowdfunding, the machines are more skilled, and you can complete much more complicated tasks. You can even translate the web, like you do in Duolingo. But it's a very big challenge to decide how to split the complicated, very big job into many tasks, and how to give incentives to the players to complete the tasks, and how to ensure that the solution is of high quality. That's it. Thanks for the extra time.